well. So the idea behind a rate-related rate is as we're looking at applications of derivatives, derivatives are rates of change. And a lot of times those rates of change have a relationship to one another. That's what we're looking at, is that relationship. So the first thing that I'm going to need to do is when I read the scenario that they give me, I'm going to need to find an equation that shows the relationship between those quantities. Then I'm going to go through and use the chain rule to take the derivative of both sides with respect to the time. Now remember when we did implicit differentiation, we took the derivative of y in terms of x. And anything that wasn't in terms of x, then we had to leave a dy dt, or sorry, a dy dx in there. It's the same idea here when we go through and take the derivative in terms of time or with respect to time. Anything that is not in terms of t, I'm going to have to leave that derivative in there. We'll see that in just a second. And then number 3, we'll go back and we'll plug in the known values that they give me in the problem, and then we'll solve them for any remaining unknowns. And if I've done this correctly, there will only be one remaining unknown, and it'll be the one thing they asked me to find. Always nice when that happens. Now, number 3 is plugging in these known values, but there is one exception to that. We typically do not plug in the values that they give me until after I differentiate. The exception to that is when the value that I'm working with is a constant. If the value that I'm working with is a constant, then I'm going to plug it in before I differentiate. If it's not a constant, if it's a varying quantity, which the majority of them are, then I plug that in after I differentiate. So let me show you what I'm talking about. Example 1. Example 1 says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So if in my problem I have a spherical balloon and they talked about a volume and a radius and a diameter, then I need a volume formula for a sphere. Now the nice thing is on the AP exam, they don't give me a formula sheet like they do like on AP Physics. They don't give me a formula sheet. They will literally give me the formula that I need for the problem that I am working on. If it's an abstract thing, you know, they're not giving me Pythagorean theorem, but if it's something like the volume of a sphere, then that would literally be sitting there in the problem given to me. All right, so that is my volume formula for a sphere. So we found the equation that relates the quantities. And then number 2, we're going to use the chain rule to differentiate both sides with respect to time and then plug in the remaining values. The only time that we plug in the values before we take the derivative is if I have a value that's a constant. So I want to look at the one value they gave me. They gave me a diameter of 50. If the diameter is 50, then of course the radius is 25. As my balloon is inflating, is that radius going to stay constant at 25? No, it's going to change, right? So that's not a constant. So I am going to go ahead and differentiate first. I won't plug in the 25 until after I differentiate. If it had been a constant, I would have plugged it in before. So let's go through and take the derivative of both sides with respect to time. So if I do that, the derivative of volume is going to be dv dt. Because volume was not in terms of time, I'm using chain rule here where I'm saying, okay, the derivative of v is just 1, but since that was not in terms of time, I have to leave dv dt in there. Everything in here is going to be in terms of time. All right, then on the other side, if I go to take the derivative, remember that 4/3 pi, that's a constant. I mean, pi's a number, right? So if you have 4/3 pi sitting there, that's just as if you had a 5 sitting there in front of that. If you had 5r cubed, you would say 3 times 5r squared, right? So we're going to do the same thing. We're going to say 3 times 4/3 pi r squared. So if I did 3 times 4/3, that would just leave me with 4 pi r squared. Then the r was not in terms of t, so I have to leave a dr dt in there. So I've taken the derivative of both sides using chain rule and done it with respect to time. So now number 3, let's plug in the values that they gave me in the problem. So here's what they told me in the problem. Air is being pumped into a spherical balloon so that its volume increases at a rate of. That's rate of change of volume, right? Volume increases at a rate of. That's rate of change of volume, and it says that that is 100 centimeters cubed per second. So the rate of change of my volume is going to be 100 centimeters cubed per second. You can see that genuinely is with respect to time. Then it says, how fast is the radius increasing? So that means that I want to know the rate of change of the radius. How fast is the radius increasing when the diameter is 50? And we've already talked about if the diameter was 50, then the radius would be 25. So I can come over here then and plug in my known values. I know dv dt is 100. I know my radius is 25. So the only unknown that leaves me is dr dt, which is good because that was what they had asked me to solve for, right? So if I've done this correctly, there'll only be one remaining unknown. It'll be the one thing that they've asked me to find. So now I can just solve for that guy. So I could go through and say 25 squared times 4 is going to give me 2,500, and then times our pi. I don't want to go ahead and throw that into a calculator and get a decimal approximation. Unless they tell me to give a decimal approximation, I always want to give the exact answer. And if they do tell me to give a decimal approximation, I need to give at least 3 decimal place accuracy. All right, so let's divide both sides by this 2,500 pi. So when I do that, I could reduce that down. So 100 over 2,500 gives me 1 over 25 pi. And I also need to give a label for my answer. Now, the way that I label my answer is it's just going to be whatever my radius was being measured in over whatever my time was being measured in, because this is dr dt, right? So my radius was being measured in centimeters and my time was being measured in seconds. So my answer would be in centimeter seconds. Related rates is one of those topics that the more you do, the better you get, and the more that it makes sense. So we are just going to do example after example after example after example, and then the next time you see one like it, then you would have an idea how to approach it, right? Something else that I want you to get into the practice of doing is, as you read the problem, go ahead and pull out any information that they give you and label it, because when it comes to our test, I'll literally give you 1 point for everything that I see labeled there. So, you know, if it's like a 10-point problem, you can pick up 4 or 5 of the points just by identifying the information correctly, and a couple points for taking the derivative correctly, and a couple points for plugging those things in and giving the answer with the correct label, that type of thing. So get in the habit of labeling each of your quantities and listing them so that you can pick up points for those, and that's true on the AP exam as well. All right, example 2. Example number 2 says, a ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so here's my wall, here's the ground, here's the ladder leaning against the wall, and the ladder begins to slide. So it's sliding down here, and if it does that, then this part of it is going to start sliding out this way, is what they're saying. So it says a ladder 10 foot long. So I'm going to go ahead and label this 10 feet long. Rests against the vertical wall. The bottom of the ladder slides away from the wall at a rate of. That's a rate of change, right? So it slides away from the bottom of the wall at a rate of 1 foot per second. So whatever you might have this labeled, I have it labeled x. That distance is changing at a length of 1 foot per second. So I could say dx dt is equal to 1. Then it says, how fast is the top of the ladder sliding down the wall? Okay, so whatever you labeled this over here, I called it y. We want to know the rate of change of y. We want to know the rate of change that this distance is, or that length is changing. So I could say, okay, what's the rate of change of y with respect to the time? That's what I'm trying to find. When the bottom of the ladder is 6 feet from the wall. Okay, so at the instant when x is equal to 6. Now, they did not tell me y is equal to 8. But there is enough information in this problem that I can figure that out. Because if my ladder is 10 and x is 6, Pythagorean theorem would enable me to figure out that y is 8. I may not think to do that right here, but when I get over here and start solving my problem in a couple of minutes, I'll point out to you when it would have prompted you to go look for that if you didn't think to do it in the very beginning. All right? So we need, number one, an equation that relates these quantities. Well, that's a right triangle. So we could do Pythagorean theorem, x squared, a squared plus b squared is equal to c squared. So I go back and look. Remember that I'm going to plug in values after I differentiate unless I have a constant. So I go back and look at the numbers that I had. I had 10, 6, and maybe I have already discovered 8, or maybe I haven't. So are 6 and 8, are they constant or are they changing? They're changing, right, because this length is changing as the ladder slides down the wall, and this length is changing as the ladder slides out from the bottom of the wall. But what about the 10? Does the length of the ladder change? No, that is a constant. So if I have a constant quantity, remember, I plug that in before I take the derivative. So when I come over to my Pythagorean theorem, which is a squared plus b squared is equal to c squared, and I plug in my x and my y, I will also plug in my 10 before I differentiate. Okay, so now I'm ready to, step number 2, differentiate both sides with respect to the time. So I'll take the derivative of x squared, that would be 2x, but that's not in terms of time, so I have to leave the dx dt in there. I'll take the derivative of y squared. That would be 2y, but it was not in terms of time, so I'll have to leave the dy dt in there. And then I'll take the derivative of 100, and the derivative of a constant would be 0. All right, so then I'm going to plug in the values that I know and solve for the only one remaining value that I don't know. So, okay, they told me that x was 6. They told me dx dt was 1. I don't know y, and I don't know dy dt, and I cannot solve for two unknowns at the same time. I know from the problem that I'm supposed to be finding dy dt, and so that's where my problem would prompt me to go back and look at it and go, okay, somewhere in this problem there has to be a way to find y, because I'm supposed to be solving for dy dt, and I have to have every other value. So if then I went back to the problem and went, how could I figure out what y is? Well, oh, this is 6, this is 10, Pythagorean theorem. Then that would prompt me to go find out that y was 8. Okay? So if I didn't find it in the beginning, I definitely would find it at this point, that I could say, okay, y is 8, and dy dt is what I'm trying to find. So I could multiply here, and I'm going to have 12 plus 16 dy dt is equal to 0. Subtract the 12, and divide by 16, and I'm going to put that in lowest terms, so I'll get dy dt is negative 3/4. I need a label for my answer, so it's just going to be what y was measured in over what t was measured in. So y was being measured in feet, and t was being measured in seconds. Now, why is my answer negative? Well, a negative quantity represents a decreasing quantity. So if you go back and you look at y, that should be negative because that quantity is decreasing as that ladder slides down the wall. So you could either say negative 3/4 feet per second, or you could say your distance is decreasing because the ladder is sliding down the wall at a rate of 3/4 feet per second. You would not say decreasing at a negative 3/4. That's like a double negative in English, right? So you either say decreasing or you say negative, but you don't say both, or they counter each other. All right, look at another one. For example number 3. Example number 3, it says a water tank has the shape of an inverted circular cone with base radius 2 meters, height 4 meters. Water is being pumped into the tank at a rate of 2 meters cubed per minute. So find the rate at which the water level is rising when the water is 3 meters deep. Okay, so again, I'm dealing with volume, radius, height, and in this case, I'm working with an inverted circular cone. So I need the volume of a cone. So again, that formula would be given to me that V is equal to 1/3 pi r squared h. There's the volume of a cone. So let's go back and identify what they told me. The base radius of my cone is 2. Okay, so here's the base of my cone. I know it seems like this should be the base, but the base is what it sits on, not how we hold it to put ice cream in it. So the base radius is 2, and it says the height of my cone is 4. So here's my height, it's 4. If water is being pumped in at a rate of 2 meters cubed per minute, what is the rate of change of? My choices are volume, height, and radius, right? So it says water is being pumped into the tank at a rate of 2 meters cubed per minute. That's a rate of change or derivative of what? The volume. And I get a big clue there, right? Because what's the only thing that's cubed? Volume, right? I wouldn't have a radius that's cubed or a height that's cubed in this scenario. So that would be a clue for me. So I could say, okay, the rate of change in my volume is 2. And then it says, find the rate at which the water level is rising. So I have a level of water in my cone here, and we're looking for the height of that water level. So we want to know what's the rate of change of the height of the water at the instant when the water is 3 meters deep. So at the instant when the height is 3. Okay? So let's think about, is anything constant that I would plug into my formula before I take the derivative? The value here of 3, is that constant? The height of the water is changing as I'm pumping water in, right? So that's not going to be constant. I'm going to differentiate first. Now, if I were to go through and take the derivative of this formula as it stands, I would get a dv dt, a dr dt, and a dh dt, right? I have a dv dt. I'm supposed to be finding dh dt. There was no information given about the rate of change of the radius. So if I go through and I take the derivative of this formula as it is right now, I'm going to get a dr dt and a dh dt, and I can't solve for two unknowns at the same time. I'll be stuck. So there must be some way in this problem that I can get rid of that radius and simplify this formula down. I have not taken the derivative yet. Because again, if I go through and I differentiate, I'm going to get dv dt, dr dt, dh dt. I have dv dt. I'm looking for dh dt. I know nothing about dr dt. I have to get rid of that or I won't be able to find dh dt. So that's how I know this is different from what we've seen so far. So I'm going to go back to the problem and say, is there any way that I could get rid of this radius in my formula? We'll go back and look at what else they told me. They told me that the radius of the cone was 2 and the height of the cone was 4. And I have similar triangles in this cone. Similar triangles would be right here. Here's one of them. That is the radius of the water with the height of the water. And then here's another one right here that deals with the radius of the cone and the height of the cone. How do I know they're similar? Well, if you look at this right triangle right here, compared to this right triangle right here, they both have a right angle, there and there, right? And they share this angle down here. So if 2 of their 3 angles are the same, then that means all 3 of their angles are the same. So in similar triangles, if your angles are the same, your sides are proportional, right? So I could say that the radius is to the height of the water as the radius is to the height of the cone. Because they're similar triangles, I could say this radius is to this height as this radius is to this height. So r is to h as 2 is to 4. I am trying to replace r. And I'm trying to get rid of that variable and replace it with something that I know. I know h and dh dt and dv dt, so I'm trying to figure out some way of replacing r with an h or a v or a something. And so you can see right here, if I took that and I solved it for r, multiply both sides by h, that'd be 2h over 4. That would give me h over 2. If r is equal to h over 2, then I can replace r with h over 2. If I do that, I'll have h squared times h, which is h cubed. I'll have 2 squared, which is 4 times 3 to give me that 12 in the denominator. And so I have rewritten my volume formula without a radius. So that when I go through and differentiate it, now I'll only get a dv dt and a dh dt because that was all the information that I had over here. how in the world am I ever supposed to know to do that on a problem? Well, the first time I saw it, I would have had no clue to do that. But when I see it 4 more times, and then I see it on a quiz or a test, then I'll know how to approach it, right? So that's what we said with these